Good afternoon, everybody, and welcome to a Ski Institute seminar. We have the pleasure of having Leo Grady here, who is Vice President for Research and Development at HeartFlow, trying to figure out when the last time he was here. We think it was around 2005 and 2006, so it's been a little while. It was soon after he got his PhD from Boston University, and then he was a research scientist at Siemens and kind of rose up through the ranks within Siemens. And a few years ago, he has moved over to HeartFlow to become the Vice President for Research and Development. And Ross invited Leo to be one of the keynote speakers at our NIH-supported summer school in image-based biomedical modeling that's taking place in Park City. And Leo was nice enough to come in a day early and spend today with us at the Ski Institute and give a talk here. And tomorrow he'll give his keynote talk up at IBBM. So please welcome, join me in welcoming Leo back to the Ski Institute.
Thanks a lot, Chris. I'm really happy to be back. And what I wanted to do today is talk about what we're doing at HeartFlow in terms of computational modeling and calculating blood flow, and how we're trying to apply that into clinical practice. And because this is a technical audience, really focus on a lot of the challenges, the technical challenges that we face in really bringing this technology to market, and dive into a little bit more detail there. So I guess Chris has already gone through this. Those are the books that I wrote, so when Christmas comes around, you know what to look for. We deal with coronary artery disease, and coronary artery disease is affecting the coronary arteries of the heart. For those of you who don't know, the coronaries are the blood vessels which feed the everyone's heart, and when one of those gets blocked, then it can cause a heart attack and ultimately death. In fact, coronary artery disease is the #1 cause of death worldwide. About 1 out of 3 people die of coronary artery disease. It's a massive social problem and economic problem as far as the amount of money that's necessary to be spent on the prevention and treatment of coronary artery disease. The clinical paradigm today is when a patient comes in with chest pain, they will receive a series of non-invasive tests, usually a treadmill test, maybe a SPECT, stress nuclear exam, stress echo, or sometimes just a risk score, like a Framingham risk score. If there's any indication of coronary artery disease, and the patient is often sent for an invasive test, which is usually an angiogram, can be other invasive tests like an IVUS or a pressure measurement. These tests are expensive, they can be dangerous, and most of the time when these invasive tests are done, it's found that the patient does not have obstructive coronary artery disease, about 2/3 of the time based on the available data. When a patient does have coronary artery disease, there are 3 treatments generally available. One is medical therapy, so drugs, medication. Another is a stent, which is a little metal tube that you can push inside the patient's artery that expands to restore blood flow. And then coronary bypass if the disease is more severe. A lot of these treatments can be very effective, but sometimes it's difficult to understand what treatment is most effective for which patient. So the treatment selection can be hard. Where we're trying to go with HeartFlow is to go in a direction where when a patient comes in with chest pain, that we create a personalized anatomical and physiological model for that patient. Use simulation-based diagnostics to really understand the origin and the severity of the disease, and then ultimately enable evaluation of multiple different treatment options to help the clinician understand what the best course of action is going to be for treating this patient. Specifically, we focus on a test called fractional flow reserve. And fractional flow reserve is a test that is used to determine whether or not a patient has a severe coronary artery disease, enough to warrant revascularization with a stent. So the way this test works is it's an invasive test. You go inside the patient all the way around, and you go to the location of a blockage. You measure the blood pressure before the blockage, after the blockage, and you take a ratio. If that ratio is below a certain cutoff, it's been shown with a number of clinical studies that the patient is better off receiving a stent. If that ratio is above the cutoff, then the patient is generally better off with medical therapy. So this is a great test, and it's been shown with these clinical studies. It's the best known way of determining who needs a stent and who doesn't. Problem with it is that it's invasive, it's expensive, it's dangerous, and about 2/3 of the time you find out that the patient does not need a stent. So this entire procedure was not necessary. The patient could have gone straight to medication. So what we're doing is targeting the same information, but doing it non-invasively with a CT scan. So what we do is we take a cardiac CTA and we extract the center lines of the patient's coronaries. Then we find all of the plaque, all of the different blockages in the patient's vessels. We extract the lumen surface. So the lumen is the part of the blood vessel that the blood flows through. And then we also extract the heart tissue, the myocardium. And taking this model together, we create a 3D finite element model, and we solve the equations of fluid mechanics to actually calculate the blood pressure before and after this blockage. And so that's what you're seeing here. That's the ratio of the blood pressure calculated at that location to the pressure calculated at the aorta. So in other words, what we're trying to do is provide the same information through non-invasive calculation that is being measured invasively with the pressure wire. When this technology was first proposed, there was a lot of skepticism about whether or not this was actually possible to do. And so there were 3 clinical trials that were done in order to validate this technology. These were multi-center trials. They were published in top medical journals, and they really established the accuracy that we were able to achieve with this non-invasive calculated FFR. And it was on the basis of these trials that we got our FDA approval in late 2014, and have been on the US market since then, and also have been operating clinically in Europe and Japan. So once you establish the accuracy of the trial, then you could say, well, what happens if you introduce this into clinical practice? So in order to address that question, we did another trial called Platform. And Platform was, we took patients that were headed to the cath lab to get an invasive study, cut them into 2 groups. And in one group, what we did is we allowed them to go through the normal standard of care treatment. The other group got a heart flow test first. And in that group, the physician could look at the results and decide how to go about treating the patient from there. And then we tracked these patients for a year and assessed what happened to them. So in the group of patients that went through the standard pathway, about 26% of them end up getting stents, and 73% of them had negative invasive tests, meaning that they could have just gone straight onto medical therapy, could have gone straight on medication without getting any kind of invasive work done. In the group of patients that went and got a heart flow test first, you had about the same number of patients getting stents, but only 12% end up going and getting a negative invasive test. 60% of the patients, as soon as the physician saw the heart flow results, put those patients straight on medication without any invasive workup. Then we followed these patients for a year to see whether or not it was safe to defer these patients from an invasive test, and looked at whether or not there was any difference in heart attack or any other kind of major event, and there was no difference between these 2 populations. So what this trial showed is that if you're going for an invasive test and you get a heart flow test first, then you get better care, better quality of life. And because of all these avoided invasive procedures, you actually save an average of $3,500 per patient by getting a heart flow test first. When you consider that there are about 20 million patients in the US every year that have suspected coronary artery disease, you see the opportunity that we have to really impact patient care and patient cost. The same study was replicated by a number of individual sites that have adopted HeartFlow and have seen almost identical results. And they've been published in single center studies. So let me tell you a little bit more about the technology, some of the challenges that we face. So the company was founded back in 2007 by Charlie Taylor, came out of Stanford working on blood flow modeling for about 20 years. Today we have about 200 employees. And the way the system basically works is like this. So the CT data is acquired at the hospital. It's uploaded to the cloud. We extract the patient-specific anatomy. We perform attach the patient-specific physiology, do the blood flow calculation, and then we return the results as both a PDF and as a 3D interactive model that you can interact with from a web browser. So I'm going to go through these different stages and talk a little bit more about the technology and some of the challenges that we face. So the first challenge is really on the image analysis, creating this 3D model from the patient CT scan. Just to give you an idea of what that looks like and why it's so challenging, here's a CT image. Here's a patient that has a stenosis, a blockage. These are two different segmentations that could be created from this image. I'm wondering, can you guys actually see what the difference is between these two different segmentations? Yeah, that's right. So the segmentation in scenario 1 is just a little bit tighter, and in scenario 2, it's a little bit wider. Now, if you're publishing an article and you're calculating dice scores or something like that between these two segmentations, they would be practically identical. I mean, we're really just talking about a few voxels difference. However, when you do the fluid calculations, you can get very different results. So in the segmentation where the stenosis is modeled a little bit tighter, we calculate an FFR of 0.68, pressure ratio of 0.68. If it's modeled a little bit wider, we get an FFR of 0.91. Now, we know the truth for this patient because they were in one of our clinical trials, and they were measured to have an FFR of 0.95. What this means, and the clinical cutoff for a stent is 0.8. So what this means is that if we have this image and we segment it like this, we've nailed the accuracy of this patient. If we segment it like this, then we've totally screwed up the results for this patient. And not every patient is so sensitive. Not every vessel is so sensitive. However, it can happen. And because it can happen, it requires us to be extremely precise, extremely consistent, and robust when we're performing these segmentations. And in fact, these are pretty simple scenarios, pretty clean image. A lot of times we're dealing with more complex situations where we have mixed plaque, we have bifurcation disease, calcified areas inside soft plaque, we have blooming artifacts, and so on. And we need to achieve that same level of precision and accuracy across all these different scenarios every time. So this is a big challenge. Additionally, we have to deal with the fact that we get, every patient is different, every hospital is different, so we need to be robust to the different scanner type, different reconstruction protocols. Different hospitals have different patient preparation protocols, variations in image quality, variations in disease. We have anomalous anatomy, and also differences in patient demographics. So it's a big challenge in terms of the image analysis piece of what we're doing. So just to give you a little taste of some of the things that we see, there's a pretty common misregistration artifact that we have to deal with. Here's a patient that had an aneurysm in their RCA. So this is about 22 millimeters across. Standard RCA is about 3 or 4 millimeters across at the root, and a pacemaker lead. Here's a patient who had an aneurysm in their myocardium, which is something that your shape model doesn't typically accommodate for. This is a patient with an anomalous coronary origin. So usually a patient has two vessels coming out of both sides of the aorta. This patient just had one where the vessel wrapped all the way around the heart, supplied the entire heart from just this one vessel. We see this kind of thing every day, and we need to build the system to be robust to it. So how do we do that? Well, the classical approach is to build a workstation where you have a toolbox, an ability to look at the images, and a set of tools to go through and do the segmentation or review and correct an automated segmentation. That works in many scenarios, but what happens very frequently is that there's significant user time necessary to do that, and that the results can be very user dependent, can be variable depending on who's using this sort of toolbox. And so what we've done is approach the problem a little bit differently. We do a cloud-based automation. So as soon as the images come in, we run our series of automated algorithms to create a full coronary tree. And then we built a custom software, which is a guided workflow, which walks our human technicians through every location in the vessel tree, provides a series of customized visualizations and tools so that they can quickly go through, but check in a very standardized way if there are any errors and make corrections in a standardized way. So I'm going to dig into these in a little bit more detail. So as soon as the images come in and hit our servers, the algorithms will find the aorta, the osteopoints, the center lines, the lumen boundaries, and the myocardium. Every series that we're sent, that gets done fully automatically and in the cloud, and then those models are sitting there waiting for our technicians to pull them down and review them. We are using data. We have the benefit as a service-based model to be able to train our algorithms and test on a wide variety of different geographic locations. Basically, every case that's been sent to us, every patient that's been sent to us, we've been able to learn from and improve the automated algorithms and improve the way in which our system is operating. Today, we've got about 16,000 patients that we have in our database with models and the personalized hemodynamics from a range of different geographies around the world. Not surprisingly, we're using deep learning to do all of our image segmentation. As I'm sure this audience is relatively familiar with deep learning. One of the key points that I'd like to make about it, though, is that in contrast to a lot of classical algorithms where you'd feed in more data and you'd get this plateau of performance, with deep learning, it's been shown that the more data you feed in, the performance tends to continue increasing and not plateauing in the same way as classical algorithms. It's great for us, something we can really take advantage of. So just to give you an idea of how we derived our system, we take the center line in the vessel, we parameterize the lumen surface using 32 directions radially around every center line point. We look at the cross sections in two directions, and we create this 3D cylindrical ring architecture that we built. We use basically leveraging what we know about vessel consistency and radial symmetry, put that into the deep learning network, and what that does is predict point location from the center line to the lumen boundary all across the surface, and then that surface gets reconstructed into the final lumen segmentation model. We put a lot of effort into this architecture and really specialized it for our problem, knowing, by using domain knowledge about vessels and consistency in vessels. There's a lot of power that you can get from that. I think there's a feeling among many people in the community that you don't have to use domain knowledge to attack a problem with machine learning. You can just feed in a lot of data and you can get a result out. That's definitely not our experience. So if you just feed in the same several thousand training cases into 3D UNet, one of the standard algorithms today, you don't get great segmentations of the 3D lumen boundaries in comparison to what we're doing with our deep learning system. So then the next question was, how do we actually know whether these lumen boundaries are accurate? And to look at that question, we used OCT, which is an invasive imaging modality that has a resolution on the order of about 0.02 millimeters. And for these patients, we have the CT data, we have the OCT data, and comparing them is not trivial because the CT data is in 3D, the OCT data is just lengthwise. So we deform the CT data, we align it with the OCT, we twist it so that we align all of the bifurcations, and that allows us to really compare the minimum lumen area from the OCT with the CT data. When we do that, using just the fully automated algorithm, we did a pilot study on 34 patients, which was about 113 lesions. The correlation coefficient between the minimum lumen area derived from OCT and what we automatically calculate from CT was 0.9. Now, if you compare that to all of the other publications in the literature, expert reads, automated reads, you get correlation coefficients somewhere in the 0.53 to 0.89 range. So 0.9 is absolutely state of the art, and that's just their fully automated analysis. Those results are then checked by all of our technicians, and each one is carefully examined to make sure that we really nail each lumen geometry accurately. In terms of absolute error, the minimum lumen diameter of the CT compared to OCT had an average absolute error of 0.21 millimeters, which is pretty amazing when you think about the fact that one CT voxel is on the order of about 0.4 millimeters. So in other words, our average absolute error is about half a voxel from CT to OCT. There's still a lot of opportunities to drive this in the future. Obviously, just feeding in more data, more scenarios is going to help. One of the things that we want to do is gather more OCT data, really take this pilot study and expand it to multiple centers, multiple scanning machines. But eventually, we want to start training on the OCT as the ground truth. So feed in the CT, train the boundary from the OCT so that we can learn really how to address artifacts appropriately. Another thing that we could do is instead of just doing the segmentation purely independently for every image, to actually integrate data across multiple different series. So if you have a soft kernel reconstruction, a hard kernel reconstruction, iterative reconstruction, diastolic phase, systolic phase, to really incorporate all of those images to create one single hyper-precise model for the patient coronaries. And another thing is just to be able to train on more of these anomalous situations so that we have the opportunity for the system to see the long tail of possible pathologies that we might get. Second challenge that we face, I'm only going to talk about this really quick, is that once we do the automation as well as we can, we want to give our technicians the ability to see errors easily, make corrections easily, but we want them to do it the same way every time. We want this to be really, really standardized. You know, if you get a blood test and then you get a cholesterol result, you don't want it to matter which technician receives your blood sample. And we're trying to achieve the same thing with the image. So when it comes in, we want to get the same results out no matter which technician picks it up and does the corrections. So to address that, we've adopted this design philosophy where we initially have the technician inspect the region of the vessel and say yes or no. If they say no, then we try to provide them discrete alternatives so that they can say, well, maybe it's this segmentation, maybe it's this one, maybe it's this one, and they can choose A, B, or C. If we're not able to provide those alternatives, correctly, then to provide a series of smart editing tools that are robust to exactly where the user clicks. And if that still fails, to provide a series of purely manual tools so that the technician can always get the right answer, no matter how complex the situation is. The idea is that the more we can keep everybody up here, the more reproducible it's going to be, the faster it's going to be to go through, but still give them the ability to really get the geometry correct if they need to. This has been really successful. There was a study that was done a few years ago where one of the clinicians that uses HeartFlow sent about 50 cases through the system twice without telling us they were the same case, and just looked at the FFR the first time and the second time, and this is the correlation that they had from the first time they sent it through, the second time they sent it through, and they published this in the Journal of Cardiovascular CT. We had very good reproducibility, and as we're driving the automation and driving the system, we expect this to continue to tighten. One of the advantages that we have as a service-based model is that as corrections are made of the automation, we can feed those corrections back into the deep learning algorithms. And because we are putting so much effort into training and the way these corrections are being made so that they're very standardized, we actually have very excellent, very consistent training data on which to train our algorithms. Really allows us to take advantage of what people talk about with this virtuous cycle of machine learning, where you have data, you create machine learning performance, you build better products that makes more people use them, that gives you more data, and then you can improve your machine learning again and go around and around. So let me tell you a little bit more about this part, the personalized physiology and the fluid simulations. The physiology of the models is based on really two principles. So the first principle is that the resting coronary blood flow is proportional to the myocardial mass. So in other words, the demand of the heart tissue is what's really driving the resting flow in the coronary arteries through a series of known relationships. The second is that the outlet size that we calculate from the vessel tells you or indicates the amount of territory that's being perfused by that vessel. So if you know that, we know that larger vessels will perfuse more territory, smaller vessels will perfuse less territory, and using that series of published relationships in the literature, we can calculate the resistance downstream from any particular location, which will allow us to set resistance boundary conditions. So what that means is that all these outlets have these lumped parameter coronary resistances at the end, and then we use sort of a standard pressure model, Windkessel model, for the aorta, and then just solve Navier-Stokes inside the 3D domain. That allows us to calculate a pressure everywhere, and then we normalize the pressure in the aorta, or in the vessels by the pressure in the aorta, to give us the FFR values everywhere. There is a series of different ways in which you can do computational fluid dynamics. I'm sure many of you are aware. There are ways that are very computationally expensive, but very physically accurate. And there are ways that are computationally cheap, but not always so physically accurate. And we face a bit of a trade-off in HeartFlow because we absolutely demand to have the most physically accurate results because these results are being used for patient care. But we don't want to pay the high computational cost associated with those high fidelity models. So we've put a lot of effort into how do we maintain the high physical accuracy of the fluid calculations while driving the computational costs down. And it's a whole talk in itself, but I can just tell you that it's been really successful. So about last year, we were at about 50 minutes to do the fluid calculation, drove that to about 39 minutes last summer, and then since March, we've been at about 13 minutes, and we have line of sight, we think, to go down to about 5, while still maintaining that same level of physical accuracy in the fluid calculations. Okay, I want to talk a little bit about the future and some of the directions that we want to take the technology. So when the patient gets imaged, we calculate an FFR. This is a diagnostic test, which can tell the physician or suggest to the physician, this is a patient that may be better suited for a stent or maybe better suited for medical therapy. But it doesn't necessarily answer all the questions. So for example, here's a patient and they've got a very low FFR, 0.39. Okay, so you might decide they need a stent, but where do they need the stent? Well, it seems like there's one obvious location right here because it's a very location of extreme stenosis, it's a large pressure drop. But if you look a little bit more carefully, you can see that there's also a blockage here and one here and one here. So does this patient need one stent? Do they need 3 stents? In what location do they need the stents? So we want to provide a tool for the physicians to look at different scenarios and say, what happens if I were to do certain things? How does the FFR calculation change? So the idea is that the physician will have this tool and it will allow them to mark this area. It was initially very high percent blocked, very high degree stenosis. And they can push a button and have that stenosis go to something else, 10%, 0% blockage. And then we can recalculate the FFR if the lumen were open to that level. Whatever the physician thinks that they might be able to achieve through different treatment options, they can type that in, and we can redo the fluid calculations on the fly in order to provide them the result of what would happen if the lumen were a different size. So in this case, if you were to change that one stenosis that was really severe, it makes a big impact on the FFR calculation for that patient. However, this is still below 0.8 down here. So you could then, look at other scenarios and say, well, what happens if I were to, change the lumen size on this whole region? And basically, with this tool, the physician will be able to look at different possibilities and use the recalculated values to inform how they may decide to go about treating this patient. There are a number of challenges here. So one of the challenges is doing real-time FFR recalculations in response to geometric changes. The other is actually doing the geometric changes themselves. So the way that we're doing this is to interpolate between the actual patient anatomy and an idealized healthy state. But what is that idealized healthy state? It can be challenging to do that. And these are some scenarios where you can have high curvature areas where there's a stenosis, or you can have diffuse disease between 2 bifurcations where it's not exactly obvious what a healthy state looks like. But through some of the techniques that we've been building, we're calculating what we think that healthy state is and then allowing the physician to move between the current state and that idealized healthy state. Another direction that we've been working on is to predict coronary plaque rupture. So the plaque rupture is really a trade-off between the stress on the plaque and the material strength of the plaque. And when a plaque ruptures, it can be a major cardiac event for that patient. We worked on this study called Emerald, where we took patients that had a plaque rupture who happened to have a cardiac CTA within 12 months prior to that rupture. And for those patients, we knew which plaque had ruptured, and we knew the plaques that hadn't ruptured. And we tried to predict which plaque ruptured against the controls of the same patients with plaques that didn't. And there have been a number of papers that have looked at CT features, plaque characteristic features, to help predict plaque rupture. Have shown some discriminative power. But what we found in this Emerald study is actually the change in the FFR across the plaque, the pressure gradient that we calculate across the plaque, is actually very predictive of plaque rupture in those plaques that did rupture versus those that didn't. So this was a study of about, on the order of about 100 patients. It's presented last year, and the manuscript's in publication right now. We want to go forward with that and really try to get a larger cohort of patients and really validate that we really can add to the plaque rupture characteristics with this drop in FFR across the plaque. So going forward, I just wanted to talk for just 1 second about the use of machine learning in medicine. AI is really hot. Deep learning is really hot. You hear about it in many different scenarios. A lot of times what people are talking about is, like IBM Watson wants to go in and say, okay, well, here's a patient. They're, 58 years old, Asian American, diabetic, hypertensive, and we need to figure out how to treat them. So you can look at millions of other patients. You can find other 57-year-old Asian Americans that are diabetic and hypertensive, and they got treatment A, and it didn't work out so well, but others got treatment B, and that worked out great. So you can say, well, this new patient is more likely to benefit from treatment B. There's no doubt that this sort of pattern recognition across a large population can help inform better treatment for patients. But what it lacks is any kind of knowledge about that patient specifically, the personalization of that patient, what's going on with them anatomically and physiologically, because not every patient in the same group is going to be the same. So I think one of the benefits, one of the things I'm really most excited about at HeartFlow is that we're also trying to look at it from the bottom up to understand what's happening with that patient from the anatomy, from the physiology, to be able to calculate what might happen for this patient under certain circumstances, and then also look across a wide population of patients to generate hypotheses that we can then try to validate and better model and better calculate what's happening with individuals. So just to summarize, I really believe that the future of medicine is based on personalized anatomical physiological calculations rather than population risk-based analysis that we've had for a long time. FFRCT is its new, non-invasive, accurate, personalized diagnostic for coronary artery disease. It's being used clinically today. About over 13,000 patients have had their clinical management impacted by a HeartFlow study. And hyper-precise image segmentation is critical for accurate FFRCT calculations and improved patient outcomes. One of the areas where I think the community of people working in image analysis is sort of underserved the scientific community is in good interactive tools to try to help standardize how interactions are made and how those results can be edited quickly and in a reasonable way. So I think more attention is needed from the community to develop those tools. HeartFlow, with this cloud-based model, is gathering this huge collection of annotated data and personalized hemodynamics that allows us to really produce better algorithms and really ultimately better serve the patients that we are helping. And in general, I think big data offers a tremendous opportunity to study heart disease and make it possible to create better products and services to prevent and treat coronary artery disease. So today, there are about, like I said, about 20 million patients that get stress echo and nuclear stress exams for suspected coronary artery disease. We envision a future in which those patients are getting CT with these personalized modeling of the anatomy and physiology to really help the physicians make better decisions for the treatment and management of these patients. So just finally, I wanted to say we are hiring. So anybody that in the Bay Area who's excellent and is looking for a job, please send them our way. But other than that, thank you so much.
Thanks. We have time for some questions for Leo. Yes.